Now we can talk about the data interpretation questions. On every GRE quant section, you're likely to see one set of these data interpretation questions. You'll usually be a chart or a graph, and then 3 or 4 questions in a row that ask about that graph or that chart. When the figure appears, there'll usually be a message something like, questions 16 and 18 are based on the following data, and so that will be up as you go through those 3 questions. The questions on the GRE data interpretation can be multiple choice questions, i.e. problem solving, multiple answer questions, or numeric entry. There are no quantitative comparison questions in the GRE data interpretation. Also, there are no new question formats to learn for the data interpretation. It's just the same old math question formats, the 3 at the top, that we've already been talking about. There's also no new math to learn. It's all the same math we have already been learning. Data interpretation tends to focus on real-world math, math that arises in real-world scenarios, percents, statistics, ratios, that sort of thing. What's different from the rest of the quant section is the skill of reading graphs and interpreting visual information. Most of these, though, are graphs you have been reading for your entire life. We will review the different types of graph, but many will be familiar. It's important to note that unlike GRE geometry diagrams, all data interpretation graphs are drawn to scale. That implies some important strategies that we'll discuss in the next video. Some data interpretation questions demand a little more time than other quant questions, and you may have to allot as much as 2 minutes for the most challenging ones. So because of all the information, these are arguably the most time-consuming questions on the whole quant section. So you want to be prepared for that. In the next video, we'll talk about some basic strategies for the data interpretation problems. Now we can talk about some data interpretation strategies. And the first thing I'll say is, why do you think human beings came up with the idea of graphs? Why do we display mathematical information in graphs? Why is it, for example, when you flip through the Wall Street Journal or the Economist magazine, that inevitably you're going to see some graphs? Or if you open up almost any scientific textbook, inevitably there's going to be some graphs and charts. Why is it that human beings are so prone to do this? Think about it. Think about it this way. Suppose I gave you a list of 100 numbers. So printed list, 100 numbers. It could be, say, monthly readings of some economic indicator for the last 100 months. I gave you this list, and then I said, find the lowest value or find the highest value. And of course, it would be a cumbersome task. It would take you quite some time to sort through a list of numbers and find which one was highest, which one was lowest. But if I gave you a graph, suppose I had a graph like this, well, then right away you could say, oh, well, it looks like that's probably the highest point. That's a little higher than this. And that's probably the lowest point, depending on how we count the starting point. But that, in other words, right away you could pick out a high point and a low point very easily. And this is because the back half of the cerebral cortex, the human cerebral cortex, is purely devoted to processing visual information. It's something called the occipital lobe of the brain. It is the world's best visual processing machine. It's the best visual processing machine in the entire universe, basically. It's absolutely incredible what we do when we process visual information. In fact, we do it so seamlessly, so naturally, we tend to take it for granted. But it's actually an amazing set of powers that we have. And when you learn to read graphs, you're really tapping into these fundamental human visual skills. So now, having said all that, we can talk about actual strategy for the data sufficiency. The big idea is understanding the story of the graph. So there's several layers here. What do I mean by this? This is something that happens relatively quickly. It happens, say, 10 or 15 seconds. You just glance it over and you'll get the story of the graph. So what's involved in getting this story? Well, first of all, you might have to read any accompanying text, which may or may not explain some things that are not clear from the graph itself. It's always important to look at the axes and notice any units on the axes. Also notice whether the axes start at 0 or some other number, and whether they increase by equally spaced intervals or some other intervals. So all those are things to notice. But the really big idea is what's going on with the data on the graph. What patterns are apparent in the data and what do they mean? Is there an upward trend, a downward trend? Does the graph start out or end relatively flat? Are there notable high points or low points? Is it a repeated pattern? So for example, if we look at this first graph here, well, it's something that starts out low and then goes up. Well, that's profits of a company. That would be a great story. Looks like they were chugging along and all of a sudden, wow, their profits really shot up. But if it were crimes in a city or if it were incidents of a certain disease, this would be a very troubling graph. Oh my God, look how much it shot up. How many more crimes there are. How many more cases of this particular disease. So in other words, the actual scenario tells you whether the graph is something very good or very bad. You should have a gut sense, kind of an immediate gut sense when you look at this, whether it's, wow, this is really good for the people, or, uh-oh, this is really bad, that sort of thing. Similarly, this graph, that would be excellent if that were cases of a disease, very infectious, and then I guess they figured out how to cure it because the cases really dropped off. But if it were the profits of a company, uh-oh, that company is really in trouble. You see, there's a story there. Now this final one, that's a repeating pattern, so that would be exactly what we'd expect if we were looking at, say, tides or daylight or seasons or something like that. But if we're actually looking at the profit of a company, that's a company who just undergoes seasonal fluctuations and is never able to get anywhere. You can imagine it being very frustrating for a company to have its profits always stuck in a certain range, to have range-bound profits. That's the way it would be discussed in the business world. So there's a profound story to any graph, and that's what you're trying to understand. And notice, just with a glance, as long as you know the scenario, just a glance tells you a whole lot of information. You could also analyze, is an increase or decrease good or bad for anyone? We talked about that a little bit. And does one factor appear to influence another? Well, this is interesting. For example, if we look at the graph on the left, as this variable, whatever that is, increases, this one increases at a slow rate, and at a certain point it just shoots up. So that's very interesting, and it definitely appears that one is influencing the other. This one's interesting because when we move back and forth along this variable, there are low values at very low values of this variable, or very high values of this variable, we get low outputs, but there's a kind of a sweet spot in the middle where you get very high values. So that's a very interesting kind of variable. It's hard to imagine, but there certainly are scenarios in the world where too much or too little is not good, but just right is very good. That's the kind of graph we have on the right there. Also, check the units in the question. They may or may not match the data, and the GRE loved this sort of switch. For example, giving you dollars per month on the graph, and then dollars per year or dollars per week or something like that in the question. So beware of ways that they might be switching up the units between the graph and the question. Check the form of your answer before you do calculations, because that will also tell you the units, tell you whether you're dealing with fractions or percents. And if the answers are spaced wide apart, this indicates that we are free to estimate. Remember our discussion of estimation from the general math strategy lessons. In general, the GRE is not interested in your ability to perform detailed calculation. It is interested in your ability to use logic and reasoning to come to answers quickly, and estimation is a big part of this. Because all the graphs on the GRE data interpretation are drawn to scale, that's a big idea, all of them are drawn to scale, we are free to use visual estimation. Also, I'll say, don't confuse numerical differences with percent differences. Now, what do I mean by that? Look at this data here. So it's clear from this data that which country, of these two countries, which one had the biggest percent increase from 2000 to 2010? Well, clearly Malugia had a 20% increase, and Laplandia only had a 5% increase. So Malugia had a bigger percentage increase. But of course, the GRE is probably not going to ask you a question about numbers printed on the page. They would be more likely to ask something like, which one had more people added to the population between 2000 and 2010? All right, well, that's tricky. So Malugia, they added 20%. So 10% of that number is 30,000. So 20% would be 60,000. There are 60,000 more people in Malugia. Well, in Laplandia, 10 million, 10% of that would be 1 million, and half of that would be 500,000, half a million. And so even though Malugia increased by a higher percentage, Laplandia increased more when we talk about number of people. So it's very important not to confuse numerical differences with percent differences. Very, very different. These are some general strategies. The most important aspects of understanding GRE data interpretation involves understanding the various kinds of graphs. The next video lessons will review these types of graphics. I'll also say, practice out in the world. Read newspapers, read magazines, especially economic magazines. Look for graphs. Practice looking at graphs. Practice trying to understand what story the graph is telling. For example, if it appears in a magazine article or a newspaper article, what's the story of the article, and how is the story of the graph supporting the story of the article? Why is it part of the article? Those are very important things to practice, especially if you need to work in your graph building skills. Now we can talk about different types of graphics. The GRE data interpretation can present information in the form of several different kinds of graphs or charts. In this video, we will discuss various categories of charts. Perhaps the easiest kind of chart is a pie chart. This is quite likely already very familiar. You probably have seen pie charts most of your life. Typically, the data interpretation doesn't present questions that depend only on a single pie chart. That would be a bit too easy. Instead, the pie charts are usually paired with another type of chart, and one breaks down a region of the other. So, for example, a slice of the pie chart might be subdivided in a bar chart, or a bar graph, one particular bar in a bar graph, might be subdivided into a pie chart. So pie charts usually appear paired with some other kind of graph like that. Another common graph is a line chart. And the lines, they connect dots on a particular graph. It could be connections by straight line segments like this, or it could be a smooth curve connecting them. Either one is a line chart. It's basically the same information. It's kind of a stylistic difference. It could appear in either form. And almost always the horizontal axis is time. This is called a time plot because it demonstrates a trend over time. Notice that this particular graph is a very happy story. What we have here is U.S. unemployment dropping more or less continuously throughout 2014. And that's very good news. That's precisely why the United States economy got much stronger through the year 2014. U.S. unemployment is a leading economic indicator in the United States economy. And to have U.S. unemployment drop, especially to drop precipitously or continuously over the course of a year, that is exceptionally good news for the economy. Now we will talk about bar graphs. The bars may be vertical or horizontal. I want to make very clear there is no meaningful mathematical difference between horizontal bars and vertical bars. It's purely a stylistic difference. In other words, it's an artistic thing, which one would look better, but there's no meaningful mathematical difference. The bars can be vertical or horizontal, doesn't matter. The bars may represent the different members of a category or different intervals of time. The big idea is that the scale is parallel to the bar, and this indicates the variable in question, and the length of the bar indicates the amount or contribution of that element. So the length of the bar is what is really important. That's where the data is displayed in a bar graph. So here's a bar graph with horizontal bars. Notice just from an artistic perspective, if we made these vertical bars, well, at the bottom, we have some long names there: banana, cantaloupe, grapes, a cup. That would space out the bars, and just artistically or design-wise, it would be kind of a mess, whereas it's much neater to design this in terms of horizontal bars. Again, that's a design choice. It has no mathematical consequences. Notice that the scale, calories, is also horizontal, and that the length of each bar gives us the calories in that piece of fruit. So for example, probably not surprising, bananas are high in calories, but also apples and pears are very high. That's a little surprising. Whereas cantaloupe and kiwi, those are very low in calorie compared to other fruits. Here's a graph with vertical bars. Here the scale is also vertical and indicates the number of sales for each day of the week. So this is a company, it looks like on average the highest sales are on Wednesday. Wednesday and Thursday are good days. Friday is really the lowest day. It's kind of a drop-off day. In a segmented bar graph, each bar consists of 2 or more segments denoted by different colors of patterns. The segments break down the overall variable into relevant parts. So for example, here we have 2 different divisions of a company. And so notice that we might be interested in just the sales of Division 1. Division 1 has its highest sales on Wednesday. We might be interested in just the sales of Division 2. Division 2, well, it looks like Monday and Thursday are pretty close for Division 2. Tuesday is clearly the lowest sale day for Division 2. But we might also be interested in the overall pattern. And it turns out, because the overall company would have the total sales of Division 1 plus Division 2. This is precisely when you use a segmented bar chart. If you'd be interested in either the number represented by the length of each individual segment, or you might be interested in the sum. And here the sum would be the total sales for the whole company. The whole company's best sale day is on Wednesday, clearly. And its slowest sale day is on Friday, even though Division 2 has better sales on Friday. By contrast, a side-by-side bar graph, each category has not 1 bar but 2 right next to each other. The 2 bars typically represent 2 different agents, and this format allows for a direct comparison. So here we have Company 1 and Company 2. Here we don't care about adding the sales because it's 2 different companies. The people at Company 1 care about sales at their company. The people at Company 2 care about the sales at their company. No one cares about the sum of those sales. So that's why it doesn't make sense to do a segmented bar graph. Here we're just doing a side-by-side bar graph. So notice Company 1 has its best sales on Wednesday. Company 2 seems to be following a different pattern. It's peaking on Monday and Thursday. And in fact, at the ends of the week, when Company 1 has low sales, Company 2 outsells Company 1 on both Monday and Friday. So very interesting patterns here. Here's a practice question with a time graph. Pause the video, work on this, and then we'll talk about this. Okay, so the yearly costs and revenue for FabCo Corporation is shown. So it looks like the costs, the purple line, that stays more or less flat along the bottom, where the revenues seem to be fluctuating wildly. They're kind of going up. There was a big drop in 2008, presumably because of the subprime mortgage crisis in 2008. And then after that, it rose steadily. So very interesting pattern. And then we're told that profit equals revenue minus cost. So that's something that you may have to know. Certainly if you were taking a test like the GMAT, you would have to know that profit equals revenue minus cost. But here the question was nice enough to tell you that. What that means is that revenue is the top graph, cost is the bottom graph, so profit is the distance between the top graph and the bottom graph. So we can see, looks like the profit is growing. It shrinks to something really small in 2008, although there still was a small profit in 2008, and then the profit starts to grow steadily from that point. After 2004, so we're not considering before 2004, in this region, the highest percent from the previous year is what year? Well, let's see, 2006, that's a little increase from here to here. That's not much of a percent. 2008, well, 2008 was actually a drop from the previous year, so it's definitely not 2008. But 2009, look at this. Here we had a profit of less than $1 million. Here we went up to about $2 million. So that is more than 100% increase. So that is a huge increase in profits from 1 million to 2 million. From 2009 to 2010, where we go from 2 million to something slightly less than 4 million, so almost 100%, but not quite 100%. So it turns out that the biggest percent profit, again, this is not, remember the difference between numerical increase and percent increase. We had a bigger numerical increase in going from 2009 to 2010. That was a huge numerical increase, but not as big a percent increase. And here we're asked about the percent. So C is the best answer here. Another type of bar chart is the histogram. Technically, hyper-technically, histograms are not really bar charts. Yes, they have bars on them, but they're actually, if you took a formal statistics class, you'd see that histograms are actually considered a different category from bar charts. We've already talked about these in the normal distribution video in the statistics module. And as I've said, although histograms have bars, they are not bar graphs because the bar represents regions of a numerical variable, not different discrete categorical variables. The heights of the bar in the histogram indicate the frequency of values. That is the number of occurrences of the values that fall in a given range. Here's a typical histogram. So presumably we polled a number of high school students and we asked them, how many hours a week did you watch TV last week? And then we got their numerical answers and we grouped them in a histogram. So notice that most of the respondents, 35 of the respondents, the largest number of respondents, responded in the 6 through 10 range. So they named a number somewhere between 6 and 10. The next highest was 11 through 15, and then there were some outliers, some very high outliers, people saying that they watched 25 or 30 or 35 hours of television in the week. So there were few respondents who gave numbers that high. And notice again, the categories are not different discrete variables. They're ranges of a quantitative variable. Numbers of hours of TV watched last week. We're just looking at subdivisions of that particular variable. So here's a practice question. Pause the video and then we'll talk about this. Okay. In a survey, 86, very important, 86 students were asked about their TV watching habits. Half of 86 is 43. And so what that means, if we divide the list in half, there's 43 below the median and 43 above the median. So between the 43rd and the 44th person, that's where the median would be. Well, let's think about this. There are, looks like 13 people in this category. And then there are 35 people in that category. So 13 plus 35 is 48. And so it means that by the time we get to 10, we're at the 48th person. We've already passed this region where between the 43rd and the 44th person. So the median has to be in this particular column here. It has to be in the 6 through 10 range. The only number here in the 6 through 10 range is B, 7. One final category of charts is scatterplots, and that's kind of a complicated topic, so they'll get their own lesson in the next video. Now we can talk about scatterplots. When each item in the population can be classified simultaneously by two different numerical variables, this is a very easy situation to represent graphically. Suppose for a set of houses in a particular neighborhood, we measured both the price of the house and the area in square feet of the house. Two numerical measurements for each house. Then what we could do, we could make a graph like this, and it'd be very easy to see the relationship. So here, every dot is a particular house. The horizontal position of the dot indicates its area in square feet. The vertical position of the dot indicates its price. And so if we know the price of the house, we know the area in square feet, we can place that house on this graph. Notice interestingly that the price starts at 0 and goes 0, 1/2, 1, 1.5, 2. It starts at 0, but the area doesn't start at 0. The area actually starts at 500. It goes 500, 1,000, so it has equal intervals. It just doesn't start at 0. So as we might expect, as area goes up, price tends to go up. This pattern is known as a positive correlation. When one variable increases, the other tends to increase. And by this increase, we mean that if we look at the sweep of the whole population, there's this kind of upward trend of the whole mass of data points. That's what constitutes a positive correlation. On average, as area increases, then the price also increases. It's kind of an average statement or a probabilistic statement. It's very important to notice a correlation is about an overall pattern in the data set as a whole. Correlation in the whole data set does not mean that the pattern will be obeyed between every possible pair of points in the set. In fact, it's very easy to find pairs of individuals that don't obey the general pattern. So the general pattern is area increases, so price increases. But suppose I look at that house and that house. Well, as area increases, the price decreases. Or if I look at that house and that house. Or if I look at this house and this house. So it's very easy to find individual pairs that don't obey the pattern. That's not what a correlation is about. A correlation is not about nitpicking and looking for individual pairs and the relationship between these pairs. It's about a general pattern in the population as a whole. That's what a correlation is. In general, the two variables will be represented on the two axes. Any variable may or may not start from a zero value. As we saw here, one of the variables did not start from 0. Each individual or item will be represented as a single dot, and its position will be determined by the value of each variable. So here, every house was a single dot, and its variable was determined by the price and by its area in square feet. Questions may ask about regions of the graph, that is, how many points are above or below such and such a value of one variable or the other variable. So for example, how many houses cost more than $2 million? So we'd be looking at $2 million and looking at the houses that lie above this line, and these points here in purple, these are the ones that are either at 2 million or a little bit more. And so there are 6 houses on this graph that cost more than $2 million. Alternately, we could ask how many houses have an area less than 1,500 square feet. Well, here we would draw this vertical line, and we'd be looking to the left of this vertical line, and of course it would be these houses here. So that's 7 houses that have an area less than 1,500 square feet. Here's a practice question. Pause the video and then we'll talk about this. Okay, how many houses have an area of more than 2,000 square feet but costs less than $2 million? So here's 2,000 square feet. They have to be over here. And here is $2 million. So we're going to say that this point here is either at or a little above 2 million. So we're not going to count that. And it's only 1, 2, 3, 4. Those are the points that fit this criteria. There are 4 houses that have an area of more than 2 million square feet but cost less than $2 million. Some of the questions just involve counting the number of dots in certain rectangles of the graph. The test also asks about correlation. A positive correlation, as we said, is a pattern in which as one variable increases, on average the other also increases. A negative correlation is a pattern in which as one variable increases, on average the other decreases. So here are some positive correlations. All 3 of these demonstrate a positive correlation. The correlation strength varies from strong to weak, going left to right. The leftmost is near perfect, so a straight line, all the points lying on a single straight line, that would be a perfect correlation. So what we have on that left graph, it's not perfect, but it's near perfect. It's a very, very strong correlation. The middle one is relatively strong, so there's very small variation from the line. Mostly those points are hugging the line very close to it. Whereas when we get to the one on the right, that's a much weaker correlation. Yes, there's a general pattern, but there's a lot of variability now. And the more variability there is, the harder it is to discern a particular pattern. Here are some negative correlations. Same thing. Near perfect on the left, very strong in the middle, hugging the straight line, and then much more variability on the right, a much weaker correlation on the right. Truly uncorrelated data shows no upward or downward trend at all. Imagine just taking a handful of pennies, throwing them in the air, and letting them land on the floor. Just a totally random array. That's what we're talking about when we talk about uncorrelated data. The graph that's given on the test will not test the subtle boundaries between weak correlations and no correlations. Either the graph will have a very clear correlation or it will have none. Sometimes to demonstrate the trend of a correlation, a graph will include something called a regression line, also known as a trend line or a best fit line, and this shows the general trend in kind of abstracted into a single line. So you can see sort of the core pattern. A regression line is a model used to make predictions about the relationship of the two variables. So for example, if we picked this value of x and we wanted to predict what would we expect for the value of y, we'd expect something that was on the line. Now, with random fluctuations, it might be slightly higher, slightly lower than the line, but on average, we'd expect it to lie on the line. Points above the line have a y variable higher than predicted. Points below the line have a y variable lower than predicted. So here's a practice question. Pause the video and then we'll talk about this. Okay, the trend line indicates for a given body mass index what the expected basal metabolic rate would be for the individual. So given say a body mass index of 30, we'd expect a basal metabolic rate right there, a little above 1600. In this group, how many individuals have a basal metabolic rate higher than predicted? So really, this is just asking us to count the points above the line. Now, this is a funny thing about data interpretation questions. Often when you actually interpret what a graphical question is asking you to do, it's something so simple that a grade school student could do. When we phrase it like that, count the points above the line, a third grader could answer this question now. 1, 2, 3, 4, 5, 6, 7. That's how many points are above the line, 7. So I point this out merely to point out, don't be afraid of the easy answer. Graphs are supposed to make things easy. And so once you interpret what a graph is asking, it may be something incredibly easy that you actually have to do to get the answer. The whole trick is interpreting it so that you figure out what it is that you have to do. But don't be afraid of the easy answer. Graphs are supposed to make things easy. In summary, scatterplots visually display the relationships of two variables over a group of individuals. The exact location of the dot indicates the value of the two different variables for that individual. Correlations, positive or negative, are patterns that pertain to a trend of the set as a whole. They're pertaining to the whole set, the whole population, not a point-by-point comparison. And regression lines, or trend lines, demonstrate the overall correlation pattern. They are predictive in nature, providing a model whereby a y variable could be estimated from a new x variable. Now we can talk about some unconventional graphs. So on the GRE Data Interpretation, it's certainly likely that you'll see some of the more common graphs, the ones that we've been talking about in these previous videos. You will also see charts of numbers, and you will see some charts and graphs of a less common sort. In fact, there is no way this lesson, or any number of lessons, could exhaust the possibility for charts and graphs you might see. You have to understand, ETS goes out looking at charts. It's searching magazines, it's searching academic sources, it's finding all kinds of examples of absolutely bizarre, unique ways to present data, and it loves to throw those onto the GRE. First of all, if you see something like this, do not panic. If this graph is new to you, chances are very good that it's new to a vast majority of people taking the GRE. If it's new to everyone, you can be guaranteed a lot of people are going to panic, a lot of people are just going to skip the problem. If you can just keep a level head, you're way ahead of the pack right there. The test will have to specify all the rules. If it's an out-of-the-box graph, they're going to have to explain in detail, here's how the graph works. Just read carefully and use the same visual graph reading skills that we have been discussing. Here's a sample graph. Pause the video and then we'll talk about this. Okay, so this graph, if you happen to have studied physics, then this graph might be familiar. If you've ever taken, say, a thermodynamics course or something like this, for most people, this will be an unfamiliar graph. And notice what we have here. We have a horizontal axis, that's volume in liters. We have a vertical axis in pressure, ATM. That actually stands for atmospheres. You don't need to know that. And then we have three different curves. Not one curve, but three different curves representing three different temperatures. And this is showing an interaction between volume and pressure and temperature. Very interesting. So now, let P be the percent increase in volume at 3 ATM from 100 to 300 degrees Celsius. So we're going to stay on this horizontal line, 3 ATM, 3 atmosphere. At 100, we're here at 50. At 300, we're right around here. We're a little above 75. Now notice also, how precise do we have to be? Let's look at the answers. 25, 50, 75, 100, 125, wildly spread out. So this is just an engraved invitation to estimation here. So I'm not even going to bother with a precise calculation. I'm just going to say we're going from 50 to 75. Of course, that's an increase of 25. 25 is half of 50. So an increase from 50 to 75 is a 50% increase. P is approximately a 50% increase. Now, the second part, Q. Let Q be the percent increase in pressure at 75 liters. So now we're going to stay on this vertical line, the 75 liter vertical line of fixed volume. And we're going to increase from 100 to 200. So that's an increase from approximately 2 to 3. 2 atmospheres to 3 atmospheres. And so that's an increase of 1. 1, of course, is half of 2. So this is also approximately a 50% increase. Notice that we're being very general with our approximations here. Well, what's P plus Q? P plus Q is approximately 100%. Answer choice D, done. So once you realize what's being asked, not very hard. Here's another unconventional graph. Pause the video and then we'll talk about this. So this graph shows over a 2-year period the weekly sales of many models of cars. And of course the models are broken up by type: sports cars, SUVs, minivans, and compact cars. And so for each one, we're getting a range. What's the most cars that they sold in a week? What's the fewest cars they sold in a week? So now the question is, the minimum revenue from all compact cars combined is closest to how many times the minimum revenue from all sports cars combined? Interesting. Let's look at sports cars first. So if we're looking at the minimum values, the leftmost values, the leftmost dots. So the minimum values in a typical week, they would sell 0 of those really expensive $75,000 sports cars. Those must be really impressive cars, but because they're so expensive, sometimes there are weeks they sell none of them. They always seem to sell at least one of the RX-3, which costs $45,000. So that's their revenue. I'm just going to write it as 45. I'm going to ignore the last 3 zeros because all these numbers have 3 zeros at the end. I'm just going to ignore those. Okay, now the compact cars. So we're going to look at the leftmost points here. So the SD Plus, which costs $40,000, they sell at least 2 of those. So that would be $80,000. The SD, which costs $30,000, they sell 3 of those. So that would be $120,000. The TD Plus costs $35,000. They sell 3 of those. So that would be 3 times 35 is $105,000. And the TD, the regular TD, costs $25,000. Their cheapest car, they always sell at least 5 of those. That would be $125,000. 5 times 25. These two add up to $200,000. 105 and 125 add up to 230. Add those together and we get 430. So that's the total minimum revenue from compact cars. And so the question really is, 430 is approximately how many times 45? Well, looks like it's pretty close to 10 times, but let's just think about this. 45 times 10 is 450. Subtract 45 from that, 405. that would be 45 times 9. So 430 is between 450 and 405. So 430 would be something like 9.5 times 45. Well, 9.5 is closer to 10 than it's closer to anything else. So the answer here is D. Those two problems were not necessarily hard once you realized the mathematics that you had to do, but they would be very unfamiliar to many folks taking the GRE. In fact, many folks taking the GRE might get to a question like that and might simply skip it. They might think, oh my God, I don't know how to do this kind of graph. I've never seen this before. They just go into a panic and they skip it. So it's very important to keep a level head. It's very important to keep a level head throughout the test, but certainly when you see a graph that's not conventional. The more demanding data interpretation questions involve two graphs, and we would have to relate these two graphs. So here's an example of this. Pause the video and then we'll talk about this. So this is a relatively challenging problem. This involves currency exchanges as well as fluctuating prices. So the currency of country of Malugia is Malugs. Malugia sells its own crude oil in this currency. The worth of $1 Malugs is shown in the graph on the right. So the graph on the left, what we have is the fluctuating price of crude oil in this strange currency, Malugs, which is the currency of this imaginary country, Malugia. In the right, we have the equivalent of $1 US in Malugs. And the question here is, in which year was the price of a barrel of Malugian crude oil least expensive in US dollars? So let's think about this. How many Malugs does $1 US buy? So say in years like this, the years that are high on the graph, those are relatively good years for US exchange. In other words, the US is buying lots of Malugs, and so it would make it easier to buy anything sold in Malugian currency. When we got to here, this is a year that it's much harder to buy Malugs. In other words, a US dollar is worth less than 100 Malugs at that point. Okay, that's the lowest. So that's when the Malugs are most expensive in terms of US dollars. So we want something that is good for the US dollar, making it good. That would be when the US dollar is high on the graph, but not necessarily the highest point, because now we go over to the price of the Malugian barrel of oil. Well, here, the US dollar can buy lots of Malugs, but the price of oil is relatively high also. So that's not necessarily a win. Yeah, we can buy more Malugs with our US dollar, but then we have to spend more Malugs to buy the oil. We're not really having much of a gain. But notice that when we're at this high point here, it's one of the lowest prices here. So this is the second highest point on this graph and the second lowest point on that graph. That's a winner, because in that year, which is 2004, we're buying a lot of Malugs with our US dollar, and it doesn't cost that many Malugs to buy a barrel of crude oil. So that's our winner, answer choice B. That is a very hard question. If two graphs appear, you will have to combine the information from the two graphs in at least some of the questions. Once again, do not be intimidated by graphs with which you are unfamiliar or pairs of graphs that combine data. Remember that this will be challenging for the majority of people who take the GRE. Simply pay attention to the rules for the graphs and the logic of the situation.